of that magnet pointing north. Why is that? What is the bigger picture here? The Earth is a magnet, yes? The Earth displays magnetic properties. That's because there's iron, we believe, in the molten parts of the Earth, and we don't really know. Okay, but the Earth itself is a magnet, a ginormous magnet. Okay, and the poles of which, by the way, are reversing in a fairly predictable cycle. So there's actually a way. It's called, I think, paleomagnetology. I don't know, something like that. But they can, by looking at, like, say, humans, especially for humans, when humans have fire, right? And they always have like rocks around the fire or something like that, or there's rock near the fire. And so if the rock has a net magnetic moment, the fire will loosen up the domains, and like little compass needles, the rocks around the fire will point to where magnetic north is at that time, right? And since the Earth's magnetic poles have been switching in a very predictable way, you can use, that's one of the ways you can date human habitation, is by the orientation of the magnetism in the rocks. Okay, so the Earth is a giant magnet. Now, Spencer was about to say the heresy. Well, what are you going to say? If the north pole of our magnet is pointed toward the north of the Earth, then the north pole of the Earth is it's got to be what kind of magnet? Say it, folks. It's got to be a South Pole magnet. Oh my God. Okay? The Earth's north pole is a magnetic South Pole. The North Pole is a magnetic South Pole. Let it be heard. Oh my God. It's like, oh my.
Look out!
Ah! Okay. Okay, demo the magnet on the pivot. I think we did this, yes? We can attract and repel. There we go, yes. Okay. There we have it. Okay. Oh, the iron filings. Oh yeah, we got to do the iron filings. I think last time I showed you the iron filings, I was saying magnetic fields or electric fields work like this, I think, didn't I?
Yeah.
Okay. Now I'm going to say this is a magnetic field, and magnetic fields work this way, right? There we have it. But the same way that you map those electric field lines, yes? Okay, magnetic field lines work the same way. The only difference is that you cannot, whereas you could have an isolated positive charge. I could take a positive charge and put it over there. My positive charge is over there. Where's my negative charge? It's over here, right? Okay. There is no way to have an isolated magnetic monopole. They don't exist. There always is a north pole and there's always a south pole. Okay? Now fundamentally, the reason for that is that all magnetism is because of a loop. Yes? Okay? Ultimately, there's electric charge going in a circle. Okay? In the case of an iron atom, there's something about the orbit of the atom, right? And it's like iron and nickel, and maybe a couple others have this property, right? That the atoms go, say, in net clockwise or net anti-clockwise in the way that they go. Okay. Now think of this loop. Okay. One side of the loop is north, the other side is south. Yes. And all the difference between the loop and that magnet over there is that the atoms are acting like loops. Yes. Okay. And so north is like a north-ness, and south is like a south-ness. Right. It's a property. It's like a direction, an orientation of it. It's hard to. Aren't you glad I'm not your physics teacher? Right? But it's like all these atoms, you cannot get a north pole all by itself, because how do you cut a loop in half? You can't. Ultimately, you're going to get down to that one atom and you cut it in half, and it's like, it's like that golden goose. It doesn't lay any more eggs or something like that. Yeah, right? Okay, so that's why there's not, you can never ever have a magnetic monopole, which is very sad. Okay, but there we have it. Right now, as a child, I deeply did not understand this, and so I got those magnetic sets where you could like build things, and you got the little pieces of metal, and you could like build little structures. Well, ultimately, I tore it apart and found the very strong magnets inside it that made it work. Yes, right, and they were actually these like ceramic magnets, and I would drop them and they would break, and I noticed that when they broke, that the pieces themselves always had a north and a south pole. Yeah? So I kept working on it. I actually took like a hammer and started like beating on the magnets, and it would break into pieces, and every little piece, as small as I could make it, always had a north and a south pole. Yes? Okay, ultimately I would have had to get down to an atom, and then still I would always have a north and a south pole. Okay, so it's, there we have it, right? It's sad, but I had this notion that if I could get an isolated north and south pole, that I could make a perpetual motion machine. It's not true, but if I could, my plan wouldn't have worked anyway. But I was thwarted by this. Okay, and then finally, the question is how do magnets pick things up? Well, they just do. You got to learn to live with it. There we go. Okay. So here's a bunch of compasses, and the funny thing is that these compasses are going to do weird things. Why are they not pointing north? Why have they done this? Actually, they are pointing north. Isn't that interesting, though? They kind of attract each other. They are magnets themselves, and so they're going to kind of attract each other like that. Okay. But sometimes you can get them, and they'll point in random directions, and that's because they're magnets. They like each other, right? Kind of like dogs when they meet, kind of a thing, right? Okay. And so, if I bring another magnet in, I will bring another magnet in. Here, let's bring another magnet. Okay. This is kind of fun. Watch this. I bring this magnet in. It's like, where's the magnet? There it is. Okay, I'm going to bring another side in. Ooh, there we go. Yes. That's kind of fun. Look at that. Which side do you suppose is this that I'm presenting to them? Yeah, it's definitely a south pole because all the north poles are liking it. Now, this is like, this model here, this is like a substance. It's made of 3 molecules, yes? Okay. Notice that in every molecule, okay, the side that is attracted to me is closer to me. Do you see that? In this case, this is a south pole magnet, and the north of these atoms are all on the side closest to me, yes? And the south that is repelled by this south is on the farther side, yes? Yes? There we go. So what is stronger, the force of attraction between south and north, or the force of repulsion between south and south? And why? Why is attraction stronger? Because it's always closer. Okay, and these molecules here, when I'm attracting this, okay, it's always oriented itself so that the attraction side is closer than the repulsion side because of, yeah, okay, and so that in that case there's always a net attraction. Now, why can't I pick up a piece of aluminium, for example? Because aluminium does not have a magnetic moment. Okay, iron does. Iron has a side that is randomly, but there's definitely every atom's got a little north and south pole. If it's not magnetized iron, they're just randomly oriented. But if it's magnetized, they're all pointed in one direction, and therefore it acts like a magnet. Okay. The point is, though, that iron has the ability to have a north and a south side to it, right? Okay. And so that side, if it's magnetically permeable or something like that, if it's soft magnetically, that side will turn around and point toward the magnet that you bring in there a little bit. And that causes the side that attracts to be closer and the side that repels to be farther. And so there's always an attraction like that. Whereas aluminum, there's no magnetism at all, and so there's nothing to reorient, and so there we have it. Yeah?
Well, what happens if you just take the magnet and go directly on top?
What happens if we take the magnet and go directly on top? It'll just point like randomly or something. Oh, look, no, it points, it's showing that the magnetic field lines are going like this, right? And like this, which is, of course, what we expect them to do, right? They're going from north to south. Like that. And the middle one is just going, I like the magnet. I can't point at it, though. Okay. Like a chicken that's been hypnotized. Okay, so here's another slide of it, right? Here's a ferrous material like iron. Okay, we bring in a magnet. It's far away, so there's no induced magnetism. And then if I bring it closer, all of the little domains inside this magnet flip themselves around so that north is close to the side that came in, the south side, and the south side is farther away. And again, the attraction between these guys is stronger than the repulsion between these guys. Yeah? Okay, and so there's a net attraction like that. I think there are materials that are diamagnetic. Yeah? Like proteins are diamagnetic. So if you put them in a field, they flip the other way. And so there's a net repulsion. You can levitate frogs in magnetic fields. Mr. Bossy, I thought this was like a rumor, but Mr. Bossy was an intern at the place where they actually did this. They levitated a frog with a magnetic field. I know, frog levitation. Did the frog like it? I don't think so. The frog is like, I would rather be in a wetlands. Okay.